Suppose you want to find a general formula for a matrix to a large power. This is a very long and boring process to do manually if you just use the classic method for multiplying two matrices over and over again. However, if, say for example, a 2x2 matrix has two different distinct lines of eigenvectors, then there is a quick way to compute this matrix to a large power that you may know, which is covered in 3 Blue 1 Brown's Essence of Linear Algebra series. However, in this video, I would like to give you a method that I've come up with to compute a 2x2 matrix to a large power for a matrix if it happens to only have a single line of eigenvectors. So, to solve this problem, we first want to find out some fact that is implied by a matrix having one line of eigenvectors that we can actually use to help us. You can think of this fact like a stepping stone in order to get to our final method. We can begin the same way as we would usually do when trying to find anything out about eigenvectors and eigenvalues, by mathematically defining what an eigenvector and an eigenvalue is. Assume that M is a matrix with only a single line of eigenvectors. An eigenvector V for the matrix M is a vector which has the property that scaling it does the same thing as applying M to it. We can represent that definition using this equation, where lambda is the factor by which the vector is scaled. Next, we can apply the identity matrix to the vector on the right-hand side without changing its value, so that we can rearrange and take a factor of v out. Now, we are not interested in the case where v is 0, 0, as this would be an eigenvector for every matrix. This means that the matrix m minus lambda I takes a non-zero vector v to 0, 0, which also implies that it takes 2 times v to 0, 0, and 3 times v to 0, 0, and every vector that is on the same line as v. This means that applying m minus lambda I will squash space onto a single line, which corresponds to m minus lambda I having a determinant of 0. Now, we can actually stop with the usual process of finding eigenvalues and eigenvectors right here. This is because we can use the fact that M shares eigenvectors with m plus ki for all values of k, including our wanted k equals minus lambda. The easiest way to prove this fact is using some simple algebra. Assume that v is an eigenvector of M. This mathematically translates to mv equals lambda v. Now consider m plus ki times v. We can expand, substitute in lambda v for mv, and then simplify. This means that v is scaled by a factor of lambda plus k when we apply m plus ki to it. Hence, v is also an eigenvector of m plus ki. The reason why we stop here is that finding the eigenvectors of m minus lambda I is very easy due to the fact that it has a determinant of 0, and m having one eigenvector implies and is implied by m minus lambda I having one eigenvector, as they both share eigenvectors as we have just proven. Since m minus lambda I has a determinant of 0, both of its basis vectors lie on the same line, say y equals gx. If they didn't lie on the same line, then we would be able to span 2 dimensions with both of them, and so the determinant would not be 0. We can call the x-coordinate of the first basis vector a and the second b, meaning that the y-coordinates of the two basis vectors are ga and gb respectively, as we have y equals gx. Therefore, we know m minus lambda I is in this form. Now, There can at most be two sets of eigenvectors for any 2 by 2 matrix. One set of eigenvectors for m minus lambda I must be the line y equals gx. This is because we found that the determinant of m minus lambda I is 0, meaning that the whole of 2D space is squashed onto a line. Since we have defined y equals gx to be the line that both of the basis vectors are on, we can conclude that the line that 2D space is transformed onto must be y equals gx. The other line of possible eigenvectors is harder to spot. This line has the property that the whole thing is transformed onto 0, 0, which corresponds to an eigenvalue of 0. We can show that this line must always exist using algebra, as this line is defined by m minus lambda I times xy is 0, 0. Now we already know that m minus lambda I takes the form a ga b gb, so we can substitute this in. Now we can multiply out the left hand side. To get the two following equations, which are actually just equivalent. This means we have found another line which is always an eigenvector of m minus lambda I. Now, remember, for the matrix M to only have one line of eigenvectors, it is necessary for m minus lambda I to also only have a single line of eigenvectors. Since we've just found two lines which are always eigenvectors of m minus lambda I, and since there are no other possible lines which can be eigenvectors, for m minus lambda I to have a single line of eigenvectors, these two lines that we just found must be the same thing, as otherwise there would be two distinct lines of eigenvectors. Since our second line was taken to 0, 0, and our first line was y equals gx, these two lines being the same thing means that all vectors on the line y equals gx are taken to 0, 0 when we apply m minus lambda I. This means that we can show that m minus lambda I squared is the zero matrix quite easily. If we apply m minus lambda I to 2D space once, then space will be squashed onto the line y equals gx. If we apply it a second time, then our line y equals gx, which contains all of our original 2D space, will be squashed again onto 0, 0. This is a very useful fact because it implies that m minus lambda I to any power higher than 2 is also 0. We can finally solve our problem now we have this fact. To make things easier to understand, I would like to show this method with a specific example of a matrix with only one line of eigenvectors. The first thing we need to do is compute the eigenvalue of the corresponding eigenvector. To do this, we can use some formulas we have already derived, starting from the definition of an eigenvector and an eigenvalue. We also found that a matrix of determinant of 0 means that our basis vectors are on the same line, y equals gx, meaning that we have the following expression. Which we can easily solve. Our original problem was to find a formula for m to the power of n when m has only one set of eigenvectors. In the previous section, we deduced that m minus lambda I to the power of anything greater or equal to 2 is 0. To use this fact, we can do the classic trick of adding something and then taking it away, and then rearranging. Now we can use our specific example by substituting in our values of m and lambda. If you know the binomial theorem, you probably can see where this is going, but I will briefly describe it to you if you don't. Say you want to expand a plus b cubed. We can take Pascal's triangle and go to the third line down, excluding the first one. These numbers will be the coefficients of a cubed, a squared b, ab squared, and b cubed respectively. Now notice that in the third row, the first number is a 1 and the second is a 3. This clearly holds true for the nth row, meaning that the first number is a 1 and the second is an n. So we can write a plus b to the power of n as follows. Where the triple dots are the rest of the expansion. Note that everything in the triple dots has a power of b which is greater than or equal to 2. However, for matrices, this only works if we have AB equals BA. This condition holds for the way we've split up M, so we are good to go. Substituting this in, we get this. Notice how everything here is just 0. This is because we have already found that the power of b in everything here is greater than or equal to 2. Since the b we substituted in was m minus lambda I, this means that we can take out a factor of m minus lambda I squared from the triple dots, which we know is just 0. Now all we have to do is simplify. And here is our solution. If you'd like to try this on another example, I've put one on screen. And finally, for anyone interested, I have a tricky question you can try up on screen. If you know a different way to solve a problem like this, try to figure out how to solve it using matrix multiplication. I will attach a hint down below.